So hello and welcome to week 10 of Introduction to Meteorology at American Military University. It's good to have you back. I want to thank you for all the kind comments and support about our upcoming adoption. That was really nice of you. So thanks a bunch. It made a difference. So this week is the kind of the fun week, especially if you're an adrenaline junkie and you like all the severe weather stuff. A big chapter, lots of content. Not a lot of learning objectives actually, so really basically we're talking about thunderstorms and tornadoes this week, kind of the classic plains, convective, severe weather. And what we have in store today, the content in the book is interesting and compelling and straightforward, and there's a lot of good stuff in there, and I don't want to just slog through the book because the book does a great job on its own. So what we're going to do is we've kidnapped my kids' Sharpies again, so we're going to do one of those silly chart exercises, and we're going to go ahead and dive into that right now, and that'll be pretty much it for the week. I didn't get any suggestions about content, so I thought we might talk about a different approach to severe weather. It's not necessarily one that severe weather experts and people that really dive into the nitty-gritty of severe weather may use. It's kind of a simplified version of the ingredients that go into severe weather. And when you pull back, in weather and climate, a lot of the big events that happen, a lot of the big impactful phenomena can often be kind of simplified a little bit and boiled down into a set of ingredients. And so we're just going to go into those ingredients, and you may be able to lay this information on top of what's in the chapter. All right, so here we go. We've got our notebook and our fistful of Sharpies and a white shirt. So what could possibly go wrong? So we're going to talk just about ingredients of severe weather, and this applies to a lot of the concepts in the chapter, and hopefully if I'm doing my job, we'll point those things out along the way. But here is something that we worked with emergency managers in Oklahoma, basic understanding of the ingredients of severe weather and kind of what goes into an analysis of a severe weather event. So here we go. We're going to come back to this frame often, or this piece of paper often, but severe weather, or thunderstorms in general, are made up of kind of two ingredients. M for moisture and I for instability. And these play into each other. They're not completely independent. In fact, more moisture, all else being equal at the surface, you're going to raise your instability. So those are two key ingredients, moisture and instability. And if you remember back to one of our earlier chapters, we talked about instability as being this situation where you have an atmosphere that really cools off rapidly, and in fact if it dries out, that adds to it. But an atmosphere that really cools quickly as you go up means that a warm moist bubble that starts at the surface will rise, and if it rises into a very, very cold atmosphere, it may stay warmer, or will stay warmer than its environment, so it'll be lighter and it'll continue to rise up, and that's an unstable environment. We talked about some of the factors that go into that, but really moisture and instability, moisture is the fuel and instability is kind of the engine of what causes rising motion. And when we talk about thunderstorms, all of these storms are convective storms, which means lots of vertical motion, lots of upward motion. That's really, you strip away the violence and the scariness and the noise. A thunderstorm is a big engine that takes warm, moist air at the surface and creates an updraft and transports it upward. And so those are ingredients for a thunderstorm. So you're not going to find thunderstorms where there's no moisture, where it's extremely dry. Then you don't have the fuel for the storm. And where you have no instability, you're not going to get that sustained rising motion, that upward acceleration that can cause a thunderstorm as well. So you need those, and those will be places that people that are tracking the possibility of severe weather will look on a map. So those are two key ingredients. That's MI, moisture and instability. And if you have those by themselves, the next thing you need, thunderstorms don't just get born on their own, but you need a T, a trigger. You need something to start the rising motion. So to mix our metaphors a whole bunch, if the moisture is the fuel and the instability is the engine, the trigger is the starter. You need something to unlock that instability, to get that rising motion started. And in the book they list 3 or 4 great examples of what causes or what can initiate this rising motion. And it's something like a front, an outflow boundary, anywhere where winds are coming together, where there's a discontinuity and you can cause a little rising motion there at the surface. And there's some good examples in there. So a triggering mechanism will unlock this moisture and instability. It will begin that initial rising motion that in an unstable environment will accelerate. And as that upward motion accelerates, the air is going to cool, it's going to condense water, and it may continue to accelerate upward. It will hold those water droplets or maybe even hailstones up. And essentially, the stronger your instability, the potentially stronger your updraft will be. So on a day with lots of instability, and you may hear the meteorologists say, wow, it's a really unstable environment out there. Well, that means there's a potential for storms with really strong updrafts. And what really strong updrafts can do is they can hold large particles, hailstones, in the air. So when there's a lot of instability, you can have really strong updrafts. That's associated with strong winds, and it's associated with holding a lot of stuff up in the air, namely big hailstones. But in all else being equal, if you have an updraft, if you have this instability situation and you release a lot of air and it goes straight up, you're going to condense water droplets and maybe hailstones, but eventually what goes up must come down. Once the weight of all of that condensed water, all of those rain droplets and hailstones becomes too much to support, if it comes straight back down, it's eventually going to come right back down on the updraft that's supporting it and kind of die out. And that is the anatomy of that first category of storms, that thunderstorms that the book describes. And those are the single cell thunderstorms. So they go up in an environment, they rain out some brief heavy rains, maybe some hail, some really gusty winds at the surface, but eventually they kind of collapse in on themselves. It's like when you hold a water hose. I don't know how long it's been since you've played with a water hose, but if you have kids, you've probably seen this happen. You hold it straight up and the water kind of collapses down on itself, and that's the way a thunderstorm goes up in an environment without the fourth and final ingredient for big thunderstorms, and that is shear. Wind shear is the fourth and important ingredient that, if you have a lot of instability, you may have a really strong updraft. But without shear, that updraft is eventually going to collapse on itself, and you're going to have a relatively short-lived thunderstorm. But shear does some magical things that help transform ordinary thunderstorms into long-lived and more severe thunderstorms. And one of the simplest things it does, before we start talking about rotation and all of that stuff, is in an unsheared environment. And what wind shear is, it's as simple as winds being different speed and direction at different heights in the atmosphere. So say near the surface you have winds out of the southeast, and at some few thousand feet up in the atmosphere you have winds out of the southwest. Well, these different wind directions and speeds will do something to an updraft as it goes up. It'll tilt it. It'll simply, among other things, tilt the updraft. And when that happens, that means this air that's flowing up into the storm rises, and the rain and particles fall out away from the source of that updraft. So just simply tilting the updraft really increases the odds of a long-lived, sustained thunderstorm. And updrafts in a sheared environment can become tilted. And he describes it really well, probably much better than using a tilted Sharpie in the book. But essentially, if the stuff that comes out the top of the storm falls down and doesn't smash the lower part of the storm, it doesn't collapse onto the lower part of the storm, this updraft can be sustained. And a lot of the multi-cell storms that he describes can occur in sheared environment, or do occur in a sheared environment. And so we went from the single cell storm that gets unlocked by some trigger. It unleashes that instability. There's a period of acceleration that carries moist air upward. As that air goes up, it cools and condenses out water and possibly forms hail. That eventually will come right back down on itself. But in a sheared environment, it's actually tilted. This is probably overly dramatic for multi-cell thunderstorms. This is a little exaggerated. But that updraft, if it's tilted, if this is the source of the updraft, this is where the surface air is flowing in, but the precipit's falling down over here, you have a downdraft that's separated from the updraft. It can last a much longer time. So moisture, instability, a trigger, and shear together can provide an environment where these stronger thunderstorms can occur. And he talks about multi-cell thunderstorms and gives several examples, and squall lines, and mesoscale convective storms or complexes, and bow echoes, and a lot of these different types of severe storms that are often associated with strong winds that come down to the surface. And then finally he gets into the supercell. And another thing that shear, if it's really strong, can do is if you have that situation where you have winds at the surface in one direction, winds up aloft in another direction, if you put air in between those, it's going to roll. It's going to cause a spinning motion. So if I have winds on the bottom of this Sharpie in a different direction is on the top of this Sharpie, before the storm even forms, it's going to form these horizontal rolls in the atmosphere. And eventually, if this rolling motion gets introduced into an updraft, especially a tilted updraft, then you have the beginnings or the DNA of a rotating thunderstorm. And storms that rotate with a tilted updraft are called supercells, and they're the mightiest kind of breed of thunderstorms. And they occur on days when there's lots of instability and lots of wind shear. And they're the storms that produce the vast majority of big tornadoes that we see. They produce the majority of tornadoes, but they also produce the vast majority of tornadoes that we see. So almost all highly damaging tornadoes occur in this kind of supercell environment. They're usually associated with supercells, and these are rotating storms that occur in an unstable and highly sheared environment that sets up a rolling motion that gets introduced into a tilted updraft. And supercells are, and all of the big, huge, we had some awful tornado outbreaks just a week ago in the end of February and the beginning of March across much of the Midwest, and there were lots of supercells going across the Midwest on those days. Supercells, he talks about characteristics on radar, and one thing he mentions is this kind of hook echo, this kind of heart-shaped radar signature. And usually when you see this, if you know there's a lot of instability and you're in a sheared environment, this kind of radar signature with this hook echo, usually on the south side of the storm, doesn't always look exactly like this. Sometimes this can be skinny, it can be very fat, this hook can be well developed, but the basic structure is a hook near the updraft of the storm. And this really indicates an area of rotation. This is the rotating part of the storm. So where you see this hook, it's often associated with rotation in the storm. Okay, so those are the kind of families of ingredients that can lead to severe weather, severe thunderstorms. If you have moisture and instability, and you have a trigger that starts an updraft that will then accelerate because of the unstable environment, then you're going to have a convective thunderstorm. And if you have lots of shear, you're going to do some special things, which are tilt the updraft, which helps the storm be long-lived. And if you have a lot of shear, it's going to be a rotating updraft, which can lead to, or which is, a supercell thunderstorm. And the rotation associated with a supercell thunderstorm can and do spawn the tornadoes, especially the big ones that we see. Not all supercells produce tornadoes. Exactly what causes one supercell to produce a tornado and another supercell in a similar environment to not produce a tornado, it's called the tornado genesis question. And I'm honestly not a severe weather expert, but back when I was in Oklahoma, that was a very big area of research. It's kind of the holy grail of some types of tornado research. Again, not really well understood. There's a lot of research, a lot of these field campaigns where you see these guys running around chasing tornadoes and taking radar images and launching soundings into the storm environment. And a lot of that research is associated with kind of trying to capture this process that will cause one storm to be tornadic or really tornadic and another storm not to be. And that's about it. Large hail, he goes into the definition of severe weather: winds of a certain speed, hail of a certain size, or tornado. Those are kind of the Weather Service definitions of severe weather. And then you see this map, a good old climatological map of where the most tornadoes occur in the country. And you can kind of see east of the Rockies, in the plains, in the Midwest, and to some extent kind of in the South are where we see the most common occurrence of tornadoes. And it's simply because the ingredients that we described as being important to tornado or formation, those occur together more often in those areas than in other parts of the country. So in those parts of the country, you have moisture. You have this Gulf of Mexico pumping moisture into that part of the country a lot. And you have instability. It's at the right latitude where you can get this warm, moist air at the surface, cold, dry air aloft. And triggers, you have a dry line that can set up on the plains, or lots of fronts in the winter, in the spring, that can trigger these situations. And then shear, being east of the Rockies, the mountain range and the geography and just weather dynamics in general set up situations where you have a sheared environment more often there than you do in other parts of the world. And that's why the plains is kind of the tornado capital of the world. And the U.S. does see a lot more tornadoes than most of the other parts of the world. So I hope you enjoy the chapter. It's a fun chapter. They're big, scary storms. I'm not a big fan of them, to be honest. I'm a drought chaser, so but a lot of people really like this stuff. There's some information about the strength of tornadoes, the Fujita scale, and the enhanced Fujita scale. It's kind of like how we categorize hurricanes. An F0 or an EF0 is the weakest kind of tornado, and F5 or an EF5 is the strongest type of tornado. And then finally, about damage. There are lots of myths out there about tornadoes, and really, in essence, a tornado is just a really violent windstorm. It doesn't suck like a vacuum, or at least that's not nearly as important as just the speed of the winds. And a lot of, he talks about some safety information. A lot of the people that die or get really severely injured in tornadoes, it's just plain old blunt force trauma. They just get beat up by stuff. So the keys to staying as safe as you can in a tornado is be be underground is the safest, but be as low to the ground as you can, where the winds are going to be slightly less fast, and there's not much stuff flying around, and cover up the important parts of your body. If you have kids, they have football and baseball helmets. Those are lifesavers. The main thing to do to keep safe is put as many walls between you and the storm as you can. And if you have helmets, chest protectors, any armor, basically anything that'll keep you from getting beat up, you really raise the odds of making it through okay. Finally, if you have time to put shoes on, that's a good thing to do too. A lot of injuries in storms are people walking out of damaged homes and stepping on broken glass and nails and stuff. So if you have time to put shoes on, that'll save you some post-storm injuries as well. Again, tornado safety is about protecting your body from flying stuff. And for the vast majority of tornadoes, F0s and F1s, just being inside a well-constructed home is going to really raise the odds of survival. And then for the stronger storms, being in the interior part of the home is going to raise the odds of survival. And then for the strongest storms, being in a reinforced room in the interior part of a home is going to raise your odds of survival. That's it for me. I again appreciate all the kind comments about our upcoming adoption, and hope you have a good week with this material, and I hope you enjoy it. If you have any questions, let me know. And other than that, I'll see you next week, and this world is better because you're in it. All right, bye.